After understanding the dynamics of market price, primarily with a framework, secondly, by deriving a time path, and thirdly, by analyzing the dynamic stability of that time path, now we are capable of numerically solving a whole process of the dynamics of market price. So here we have a numerical example in which we have a market model, and whenever there is market model, there is a supply curve and there is a demand curve. They are there with their standard notations and symbols. And then a third equation is given, which is dp over dt, that is the rate of change of price over time. And this, as you remember, it is the excess demand So this is the adjustment equation, the correct name of it, as we dealt with this equation in the development of the formula for the time path. In addition to this, what we are given is the value of initial condition, that is the price when no time has passed. That is, the price when no time has passed is 2. So we are to find the expressions for Pt, Qst, and Qdt. And we are also interested in finding if the dynamic equilibrium stable or unstable. So let us get started with its solution. This is the adjustment equation, and you remember in the symbolic derivation we substituted the values of Qd and Qs. So we are going to do the same thing in this case. Here we have the values of Qd and Qs in numerical terms, so it is easier to solve them. Further is the standard algebra that we know, that is this rearrangement, and here the variable price is gathered, all those terms, and here the terms without variable price. And then simplification is done here. Further simplification by simply multiplying this point 2 inside with this term and with that term, and we get this expression. And now in order to make it comparable with the standard form, we are rearranging it, that dp over dt, and the price variable term is brought on the left hand side. Consequently, on the right hand side we are left with 4.8 only, which is the constant term. Now this is easily comparable with the standard form of the first order differential equation. As you can see, we have compared and we have extracted the value of a and b. Instead of the general variable y, we have p as price and a is 1.6 as compared here, and b is also found and it is 4.8. Now we have to judge that out of the three cases, which one of the case are we dealing with. Primarily we look at the value of b in order to find out if we are dealing with a homogeneous or non-homogeneous case. The value of b is non-zero, that is 4.8. It means that we are dealing with a non-homogeneous case. Now we look at the value of a, it is also non-zero, so it is a non-homogeneous case with a non-zero. And we should remember the formula for this situation. Here we are, the same formula that we are trying to recall. In this case, the non-homogeneous case with a not equal to 0, we have this formula. And here the value of y0 can be substituted, yt can be substituted, b, a, and again a, and then b, and then a again. We can substitute these values that I have put in boxes or I have underlined. Very easily you can judge that which are the substituted values. B is 4.8, A is 1.6, A is again 1.6, B, and then A as well. So putting all the given values, we got this expression, which on further simplification will give us this answer. Now we can interpret this as you know that the part with the exponential term is the complementary part, and the other part is the equilibrium part. Overall, it is a definite time path because there is no arbitrary constant in it. So if it is not there, it means that we have a definite time path. It is so because the value of P naught was given, and that was equal to 2, and that enabled us to get rid of the arbitrary constant. So we can plot this. We are expecting that there will be exponential decay in it because of the negative sign of the exponent, that is minus 1.6 into t. So separately we have calculated the values of complementary function, that is the deviation, and then added it in the equilibrium value to get the time path. This is the complementary function or the deviation, and this is the overall time path, pt versus pc. So you can do it easily by putting the value of t, primarily 0 and then 1, and you will get these values as you do all of these calculations. The observation of ours on this series of values is that the value is decreasing in terms of magnitude. However, the sign is negative because it is negative deviation, and we can expect that the diagram should look something like this, that we are starting from below the equilibrium. This is why there is negative deviation. Now we add this deviation part with equilibrium in this time path equation. So we get 3 minus 1 becomes 2, and then further calculations are done, which you can do very easily simply by adding 3 in this deviation part, and you will get this. So you can see that the value is starting from 2 and approaching close to 3, and here you can see that similar can happen, that we are starting from 2, right, and this is the equilibrium. This is the equilibrium 3, and we are getting close to it. This 2 is approaching close to 3. So this is now diagrammatically depicted. As you can see, this is the equilibrium value 3, and this is 2 from where the journey started, and it is getting close to 3. It must be remembered that it should not merge with the equilibrium value because it is getting close to it. It's the concept of limit that you have studied in previous classes. So we cannot say that it is merging or intersecting the equilibrium. It is just that we cannot observe this without using any microscope, that they are not actually merging and that they are getting close to each other. So magnifying this can help us to see their movement side by side, and we can also shed some light on these remarks. In these remarks we are saying that there was negative deviation. Yes, there was negative deviation that we observed in this diagram, this time path diagram, and as the time proceeded, the complementary part, it faded away, it approached to 0. This deviation is definitely decreasing, and the time path rose and converged. As you can see, it's 2 and it is going up, right? So it rose and it converged to equilibrium, that is 3. 3 is the value of equilibrium, and convergence is taking place. So we have unraveled this numerical example, and we have tried to explain it primarily simply by solving it. As you can see, we solved it by using all the given information, simply by using the formula, and then we developed a table in which we used some hypothetical values of t which enabled us to have some values of complementary function as well as the time path, which enabled us to make a diagram of it, and that diagram verified that there is convergence and we are rising from below and reaching that point where there is convergence. So red line again is used to show the market equilibrium, and the green line is basically the time path, which is um, showing the uh, deviation from the equilibrium, and that deviation is decreasing over time, due to which there is convergence in our current given numerical example. So this concludes the series of 4 lectures that help us to develop the dynamics of market price, the framework of it, and then the time paths of the dynamics of market price, and then further the dynamic stability condition, and finally the numerical example of it. In this way, a wholesome analysis of the dynamics of market price is conducted by using the mathematical tool of first order differential equation. Thank you.